Okay, great. Hello, everyone. So today we're gonna look at axial or the chiral anomaly in 2 dimensions. And share my screen. Okay. Great, I guess you're all seeing my screen. So the basic phenomenon we want to understand is encoded in this picture here that I pulled from some lecture notes of David Kaplan, where you basically have this is a representation of the ground state for a free fermion system in 2 space-time dimensions. And what you see here is the effect of introducing a constant electric field. So the E in the equation at the bottom is not the same as the E on the y-axis of that graph. E there is the energy, P is the momentum. Because they're massless fermions, the dispersion is linear. And that's why we have these cones. And in effect, the introduction of an electric field leads to the surplus of left movers over the right movers. So Dirac fermions are basically composed of a pair of wild fermions, just like you would have in 4 dimensions. And the effect of this electric field is to lead to this kind of current, which isn't the same as the current you'd have imagined if we were just thinking about the electromagnetism of this theory. So if I coupled genuine 2-dimensional Maxwell theory to these fermions, then I would call the charge the sum of n sub L and n sub R, which are the number of left and right-handed modes of the wild fermions. But here it's really the difference that's not conserved due to this electric field. This is a manifestation of what's called the axial anomaly, or the chiral anomaly. And do you guys have a sense for what anomalies in general are? Because I can go through that. This is a pretty good example of what they do and so on. Okay, so I'll just try and explain it. So if you have a classical system that possesses some gauge invariance, so it could even be what you would normally think of as the gauge invariance in Yang-Mills theory. It's possible that when you quantize this theory, the gauge invariance is lost, or it's violated. And that is what's known as an anomaly. This could also happen to just a symmetry of the system. And when it's just a symmetry, you're not as worried. But when it's a gauge invariance, then there's reasons to worry. That means your quantization is not consistent. It just means that you have a quantum theory of something else, not what you wanted to actually get. So famous examples are the while and mixed anomalies of the superstring, and there was something called a superstring revolution that came about when people figured out how to cancel these. Of course, the standard model also possesses certain mixed anomalies, and their cancellation in triangle diagrams was also an important discovery. And well, there's also the chiral anomaly in the electroweak sector, which manifests itself, and it gives the eta meson its mass. That's an intricate and interesting story that we can get to after we cover some basics. But for now, we'll just be interested in this invariance called chiral symmetry, and we'll look at the setting where it's we'll look at the simplest setting where it manifests, which is with these 1 + 1 dimensional fermions. So I'll start with the free theory, and then we'll see what the implications are for interacting theories and so on. So quick recap of what we need to get to fermions. We need a representation of the Clifford algebra. And here, that'll be given by these two gamma matrices. You can check explicitly that they would satisfy this anti-commutation relation. Note that we're in Euclidean signature, so you won't be seeing as many eyes as you're used to. And this theory will be coupled to an external gauge field. That's what A mu here is. It's the vector potential for some gauge field. But I won't explicitly consider the action for that gauge theory for the time being. It's just there in the background. So what this means, so generically, we say that a theory defined by some action has background fields when they more or less act like sources. So say I'm in some number of dimensions, it doesn't really matter. Then I have some fields, and so there's some Lagrangian for these fields. I'm not going to be specific about their spin or whatever, but basically, I treat these sources as external. So in principle, they could just be sources for the fundamental fields themselves, or they could be sources for composites of the fundamental fields. And if we're interested in currents in fields that have mattered, then we could say that we have fermions represented by some psi. And the current here usually, okay, sorry. So this J sub mu is what you normally think of as the current. And that's the composite that would couple to this external gauge field, A. So this depends both on psi and A. And the significance in the classical theory is a little bit hard to see. I mean, it just looks like you have another field. I mean, you don't quite have equations of motion for this field unless you have an action that gives this some dynamics. So that's one way to see it. But in the quantum theory, you'll find that the partition function depends explicitly on A. So the partition function is a function of A mu, right? Which means that if I were to do this formal path integral, so let's call it PSI, with this action, then the effect of doing this functional integral only removes the dependence of this on psi. So it still depends explicitly on A.
So, sorry if I just butt in for a second.
Yeah.
You just remind me what a current is. It just something that acts, so it's a functional on forms, right? A current.
Well, for now, it's just a special case of the f of phi that I wrote in the previous expression. So more generally,
it's act differential forms of type.
So current would be sort of top degree -1 form, because the gauge field is a 1 form, and you want these to be top forms. So the current would be a top degree -1 form, and I'm taking the Hodge dual of everything so that I can write this as a scalar.
So do you also allow something like, I don't know, forms with logarithmic growth or something, or only smooth forms? Or?
Well, classically, for the most part.
I mean, you wouldn't have it, right?
I mean,
Yeah,
no, so strictly speaking, at the quantum level, these are some weird operator value distributions. All kinds of things can happen, but
Right.
yeah, classically, you would just say that they're smooth.
right.
Yeah.
Yeah.
So I mean, so when you consider currents, you're not considering just the stuff that comes from forms, right? I mean, every PQ form gives you also a PQ current where you just wedge it and integrate, right? So you have other classes of currents coming in, which aren't exactly smooth. So yeah, I mean, it's not important. It's just I was just wondering
You
whether the
could.
class of currents. Yeah.
Yeah, no, you could. It just
Okay.
depends on what you're trying to study. So, okay, so note this theorem connects the conservation laws you derive from these currents, which is the statement that that the Hodge differential acting on them vanishes. Or not even the Hodge, really just the Dirac differential acting on them vanishes. To symmetries, in other words, it tells you something about what bundle you're putting over your space-time,
Right.
your base manifold. So in the case of electromagnetism, the conservation of this current is telling you that you have this U1 bundle, right? And roughly speaking, you could say that, well, I mean, I don't quite know what you'd peg the charge to, but you get the idea that there's some significance given to the number you get by integrating this d-1 form over some codimension 1 hypersurface. You call that the charge. And the intersection number between that object and other point-like objects is what you would call the charge of some operator. So this is what you would generally do. So if you want to measure the U1 charge, then you take this d-1 form, you find a codimension 1 surface, integrate it over that, and then you ask, okay, what's the intersection number between this object, which is topological, so you can move it around however you like. So small deformations. So the statement of conservation is just a statement that small deformations of the surface don't do anything. And then the interesting information you get out of this is what happens when you wrap this surface around operators, sort of inserted at a point. So the intersection
Sorry, I
number you
didn't
get,
catch that. So intersection number between your codimension 1 hypersurface and what exactly?
whichever operator you like. So operators are local for the most part. They could be non-local, but yeah, so whatever operator you like is supported on some stratum. And then you look at the intersection number between these two things, and that's what you mean by charge. This is a sort of highfalutin way.
The support of the operator.
Yeah, exactly. In support of the operator.
Okay, and so I mean, you need them to intersect properly in some sense, right? I mean, I mean, a smooth manifold or whatever, complex scalar manifold.
Yeah. So
Okay.
you really think that these are like some cycles, and that there's some homology that sits behind all of this. Yeah, so this is just a highfalutin way of explaining Gauss's theorem, right? So it's like saying that so you can look at the flux coming out of some surface, and that tells you something about the charge. So
And then you have the continuity equation. Yeah.
Exactly. So the continuity equation, which is a conservation equation, is telling you that you can sort of wrap the surface around whatever you like. As in, you can deform the surface at no cost.
Right.
Yeah. So anyway, this is a bit of a digression, but it's important that we did make the connection between current conservation and symmetries or gauge invariances, because that's what we'll be interested in. So in this theory of free massless fermions in 2 dimensions, with this external gauge field, we look at these chiral symmetry transformations. So I'll define a gamma 5 here, but that's just to sort of remind you all of what happens in 4 dimensions. Gamma 5 here is just a product of gamma 1 and gamma 2. So there's not all 4 that you would use to form gamma 5. But it is how you represent the action of it's basically how you represent the chiral projector in terms of the gamma matrices. So 1 plus or minus gamma 5 is the projector onto the left or right-handed parts of the Dirac spinor. And as you can see, I'll really allow for these transformations to be local. So alpha is a function of space. This is what you generally do when you ask about gauge invariances. So this really looks like a gauge invariance as a theory. Now, going back to the language we were discussing before, for Ben's benefit, having a gauge invariance versus a symmetry is that you're restricting your attention to only those operators for whom this intersection number is 0, strictly. So it's like so under a gauge invariance, if you wanted to think of it as a symmetry, it's a symmetry where everything is neutral. You can't have anything charged under a gauge symmetry. Okay, so now classically you can work out how the action changes under this transformation. It only affects your fermions and not the gauge field sitting inside this d mu. So you could just work it out to linear order in alpha, in other words, infinitesimally. And you obtain this total derivative. Now, we're assuming that there are no boundaries of the space on which we're putting this theory, which means that this is just 0. So the classical theory is invariant under these chiral symmetry transformations. So this chiral symmetry is really an invariant, like gauge invariance of the classical theory. And you can represent this through the conservation of what's called the axial current. So the axial current is given by this bilinear in the fermions. And you can really see that the vanishing of this for arbitrary alpha requires the vanishing of the divergence of J. So basically you can obtain this current by sort of functionally differentiating with respect to alpha, or this conservation. So are there any questions about this? We've just established that this chiral symmetry, which tells us that we can rotate the left-handed fermions in one way and the right-handed ones in another way, in an arbitrary space-dependent way, is a gauge invariance of the classical theory.
So it's essentially like, is it the polarization of the magnetic field or something like that?
No, there's no magnetic field here at this level. Okay. So we're just saying that there's some. So how would you normally introduce gauge invariance? So just let's go back to the textbook way of doing this. So in the textbook way of doing things, you would say that I have matter fields that transform in some position-dependent way under some symmetry, right? Mm-hmm. And then I would introduce these gauge fields in the kinetic term of these matter fields so that they transform in a way to compensate for this position-dependent invariance. Right? So here I'm doing the same thing. So this is not about the magnetic field or whatever. Right now it's just being able to rotate left-handed while spinors one way, right-handed. So we could go back to what we were discussing a couple of weeks ago about the massless Dirac equation in any even dimension. So you always have the Dirac spinor splitting into these Weil spinors, right? And then if you have no mass, it's as though you just have two independent Weil spinors, right? Satisfying their Weil equation. Right? So you see, clearly it doesn't matter. I could just I could treat them as independent. That's essentially the idea of the axial symmetry.
So the space you're working over is actually projectivized, right? So it's the projective complex scalar manifold.
Well, you mean the total space? Oh, the Hilbert space. Oh, we're not there yet. This is still. So these are still fields living. So this is still just some, I don't know, some associated bundle over R2 for our purposes. We're not at the quantum theory.
So, I mean, to define an intersection number, you're actually using this theorem of Chow, which says that if you're an analytic submanifold of something, of a complex projective Kähler manifold, you're actually algebraic. So then, because you're algebraic, you can do intersection theory.
No,
if you're just analytic, right? If you're just analytic submanifold, you can't do intersections.
No, but
I mean, it's not
can
well
I just say, yeah, but can I just say that I have the DRAM complex basically, and then I can do the, what is it called?
Yeah, I mean, you get the Dirac
Poincare duality to the, so all I'm saying is I take the Poincare dual of some form, and then I get some cycle. And then basically I can rewrite Stokes' theorem in terms of the intersection number between these two cycles, right? I mean, appropriately defined cycles.
But the cycles will be algebraic, right? I mean, you don't want analytic cycles. Yeah, analytic intersection theory is still unknown. There's still big doubts, right? So I mean, yeah. So you can't do proper intersection analytic subvarieties. Yeah. So it's just a point that, yeah. So Charles theory, yeah.
So I'm not sure where the jump, where the jump to a scalar manifold sits implicit in all of this. But all I'm saying is that I have some, so J, which is really so this is going to be a D-1 form over like really R2.
Well, so if you're living in a complex manifold, complex projective, whatever, if you're projective, then you have a natural Kähler structure, right? You get it for free.
Yeah, I mean, I just don't see why this is a projective manifold at this level. So right now it's still, right now it's just, you just have these fields and their jets living over some real manifold.
Okay.
So you don't have to phrase it as the section number. So really you could just phrase it as, in terms of the forms, I mean, I'm just integrating, you know, forms against some submanifolds, if you like, and then I'm obtaining whatever the number that comes out as a result. I'm just saying that in principle, I could, you know, using the Dirac delta function, I could define, well, I mean, I could sort of define the support. You see what I'm saying? I could define a form which looks like the delta function supported only on some submanifold integrated against the manifold, the total R2.
It's a current. So the Dirac function gives you a current.
Exactly. So basically, this is the kind of correspondence I'm using to talk about this intersection number story. But there isn't much more to it than that. I mean, at this point, really, you're only just looking at intersections between points and sort of D-1 cycles. Or sorry, ones. I'm not sure how the counting goes, but you know what I'm talking about. I'm talking about like intersection number between like the co-dimension 1 manifold and a point at most. So you have what are called higher form symmetries, where you look at the intersection number between sort of higher co-dimension surfaces. But right now we're not looking at those. So those would be the ones associated to line defects or surface operators or whatever. But here we're just interested in.
So what's interesting is that these intersection numbers actually give you a physical quantity, right? You call it charge.
Yeah, exactly.
Okay, so that's something new, right? I had no idea.
I mean, this is a perspective that I only understood better once I read into I looked into this higher form symmetry literature. It's a bit new even in physics. So it came from the world of topological order. It sort of spread all the way into high energy physics, but it's sort of a secret revolution. I mean, there's some people that knew this all along, but it's a perspective that's only been sort of spreading more recently amongst our people. Yeah, so anyway, as I was saying, for now, are we all content with this classical sort of axial invariance of the action?
Yeah.
So now let's see what happens if we try to do this quantum mechanically. Right? So these are just three fields, which means that the path integral is in principle something we can define. We can use mode expansions and then just do essentially lots of Gaussian integrals. And that's what we will try now. Right? So we have a mode expansion.
Instead of trying to quantize the free field, we're just assuming that modes exist and then like dealing with the modes right away, right? Like modes which have like coefficients that correspond to chirality, and then we're dealing with those two.
Well, I mean, we're not assuming that. I mean, it's what you would do normally. It's just that you're doing it in the path-integral picture instead of the Hamiltonian picture. So instead of like thinking in terms of, I mean, you could think of this as an expansion into creation and annihilation operators if you wanted. But you could just be more abstract. I mean, you don't have to commit to a certain form of that expansion. You don't have to use plane waves. So for now, you're just saying that you expand these fields in terms of some modes. So you expand them in terms of these Grassmannian coefficients, A, I, and BI. So what do I mean by Grassmann valued coefficients? I mean that AI squares to 0, and so does BI. So for any I. And they anti-commute among each other. So A
is equal to B.
Yeah. So if I have AI, AJ, oh no, I mean, if I and J are different, then basically I have minus J, AI. And same for B.
This I had quite a difficult time understanding Grassmann variables. So at the end of the day, it's like I just made peace with the fact that it looks something like, okay, you have some kind of a delta function around 0, and then it represents some sort of a minuscule value on that point, and then that's it. So
I mean, I don't know. I don't think that Grassmann. Yeah, I mean, I don't really think that they're distributional or anything. Like they're not really a delta function or anything.
Yeah.
You really have to think of them as, so okay, this is what you would call superspace, or in Band's world they call this a grading. So you can have gradings of higher degree. In other words, this is just be degree 1, but yeah, it's also called a superspace. In physics you call it a superspace, but you think of these as sort of axiomatic properties of these objects, and then you just manipulate them as such. So you can just use, okay, they satisfy this weird.
So it's just you have your vector space, and then you take the first wedge, so that's your first thing, and then you take the second wedge, and then you sum over all of them, right? So that's your Grassmann algebra.
Yeah.
So I mean, it's not particularly. I mean, it's not something difficult, right?
Yeah, but sure. But I mean, it's not always thought of in terms of just the exterior differential forms, right? I mean, you could have these superspaces that are just defined more abstractly, or at least you see that in the literature. But here you're right. If I was just looking at R2, I could just take, the wedge product, and I could define these. I mean, you could essentially do that even in these more abstract cases. It's just that there's some bells and whistles. Still, for our purposes, these are going to be our coefficients. These would be what you would call creation or annihilation operators. Since we haven't picked the time slice, we're not going to distinguish between creation and annihilation. We're just going to write all of them as AI. And these, there's a typo here. These psi i's are the eigenfunctions of the Dirac operator. So I was struggling to get the LaTeX editor on this typora to get the slash notation right. And that's why I'm writing gamma mu d mu everywhere. Otherwise, you would write this as d slash. So yeah, size of I has eigenvalue lambda I. The form of these eigenvalues doesn't matter for this discussion. And the set is complete and orthonormal. That's what this other expression is trying to convey. And so you can actually write down what this formal path integral measure in this setting should be. The formal path integral measure is just the product over all of these, the d of all of these coefficients. So this would be true no matter which free theory you're considering. Even if you had bosonic fields, you could write the path integral measure for free fields in terms of just a product over the,
Okay.
you see the ordinary measure with the coefficients. And so here we're interested in the chiral transformation properties of this, of the resulting expressions. I'll eventually stick this into the action. So I don't think I've written down the path integral, but the path integral itself, oh, sorry. It's going to be something happened.
It's product, yeah. Which is the basic, yeah.
S, so S being the action. So, well, let's just write it here. X. Right, so now what we can do is actually write this as something a little bit more concrete. Minus I. So there's going to be a sum over the I, so I'm just going to lower this index. And well, this is going to be the same for BI. Okay, so well, this is still lowered. So really, I want to say that there's a sum over I. Right, so this is a Gaussian integral, basically. This is just product of Gaussian integrals. And so we can, okay, but we know how the action transforms under chiral transformations. That wouldn't change, just because you did a mode expansion. The question is how the measure transforms. So, you know, in terms of these fields, we just say that under a chiral transformation, I can define new coefficients, A prime and B prime. And then you just have to work out the Jacobian between the old measure and the new one. Right? This is what you would normally do if you were doing an ordinary integral. And again, the reason why we're looking at free fields is that you could actually write this down. I mean, abstractly, there would be a measure. I mean, for interacting fields, we don't actually know what the measure is. We had another series about how in physics you get away without ever having to define it, thanks to perturbation theory, knowing how to integrate parts. But there too, you can actually make sense of what would have been the Jacobian, and that's a bit more involved. We could try and go back to that. But here, you just have this representation of the measure, so you could work out what the Jacobian is somewhat explicitly. And well, what you find is this expression here. So psi dagger is different from psi bar because remember when you take psi bar, you have to multiply by gamma 0 or gamma 1 in this notation. So psi dagger gamma 0 is going to be psi bar. So here we just don't have the gamma 0 part. And that's,
yeah. So this is like something what you would, something on the lines of what you would expect the integral of a Rachmanian to do, right? Like
it doesn't have to be Rachmanian. So what I'm saying is that if I just, so say I had a symmetry transformation. So say I'm interested in an ordinary integral of this form, right? And then I have some symmetry transformation. G of x, which I'll call y. Then you know how to write this integral in terms of y. Right? Yeah, you're just going to use the fact that the measure would transform under the Jacobian, and you just have G prime inverse f of y essentially. Yeah, so that's basically what's going on. For band, you're basically trying to work out the pullback of this form under this transformation, defined locally like this. So yeah, we're just doing this mode by mode. And here, what you're going to get for this, so okay, this is just convention that you'd have determinant to this to the negative second power, right? It's just you're defining one determinant per measure, like for A and B. If you had just one field, you'd have had determinant to the -1. So anyway, what you get for this determinant, where you can use this formula relating the determinant to the exponential of the trace of the log, is the following expression. And you might not see it here, but you're actually doing the sum over all of these eigenfunctions. And as such, this is just divergent. This is some feature of having this Dirac operator and spectrum on some non-compact manifold. I don't even think that on a compact manifold, this spectral sum would converge necessarily. It depends on the properties of the operator. But here it just diverges. So you need to regulate it in order to be able to define it, right? There's a free theory, but you still need to be able to regulate it in order to be able to define or to understand the transformation of the measure under these chiral transformations. So you see, once you write it as an exponent, you could think of it as just being something that you can add to the action. Because remember that the integrand of the path integral is some exponential function like this. So you could just think of this extra term as, we'll call it the Jacobian action, or whatever you want, just because you could write it as an exponential. So this also means that when we work out the chiral symmetry transformation of this term to first order in alpha, it will just add to what we already worked out with the action. So they're sort of on equal footing now. And this is just to say that there will be a contribution to what we were thinking of as the word identity from before, or the current conservation from before. Okay, so now we'll see that there is such a thing as the axial anomaly, that's a spoiler, but also that it really comes from having to regulate, and that this is why quantum theories reliably produce these anomalies for you. And we'll try and meditate on the implications of the same phenomenon arising from the lattice. Here we're just doing free fields, but if you had interacting fields and they're strongly coupled, you'd have to put the theory in the lattice. But the lattice too is beholden to the fact that there's a chiral anomaly. First, let's just go through this calculation. So to regulate this divergence, it turns out that neat covariant trick is to introduce the heat kernel for this operator, right? So in general, what the heat kernel is, it doesn't matter. For now, just see that if I take m to infinity, this is like inserting 1. Okay, but do that at the end. Take the limit at the end, as you would with every regulator. And so you have a few lines of plug-in chug. Now I've done this very generally with general indices because you don't have to do this in 2 dimensions. We could have done this in d dimensions. And I'll tell you how the result generalizes. But we'll specialize to the case of 2 dimensions where you see all these indices might hide the fact that there's only one component that you get. So you just get d squared plus a quarter. Now my computer is really slow for some reason. So there's just one generator of what would have otherwise been the Lorentz group, because you just have SO2 here, U1. And then the generator we call sigma 1, 2. And you would have F1, 2, which is really F0, 1, remember? Yeah, we just call the time index 0. Otherwise we could call this 1, 2. It's just a notational thing. And you know what F01 is, it's the electric field. Remember, when you have the electromagnetic field strength, the 0, 1 component is going to be the 0I components are the electric fields, and IJ components are the magnetic field. Right. So turns out that at the end of this regularization procedure, the end result, again linear in alpha, is just epsilon f. In other words, f0, 1. Right? So this is the first Chern class of the U1 bundle over R2. In principle, if you had done this in D dimensions, where D is even, then you would get the D over second Chern class. And otherwise, everything would follow the same way. D over second Chern class would involve D over 2 factors of this F that essentially was together and contracted. So you will see this written as trace F. I just didn't do it here because you might get confused. I mean, there's an epsilon, why are you calling it a trace? Remember that F is antisymmetric, right? So if you just took the naive trace, then you're going to get 0. Right? So if you have antisymmetric forms, the real trace is going to have to be with the epsilon sign. And you get the final result. So you get the expectation value of what we had before, right? The divergence of this chiral, this axial current, right? Which is still, okay, so let me just make this a little bit less cryptic so that we can see that this is the same as what we had before. Oof. Anytime. Okay, now it's working. Five. Sorry. Yeah, our old axial anomaly. Note that you can just take the derivative out of the expectation value because, yeah, the dependence on space is sort of unintegrated in the path integral measure, and you get this this expression. So our old axial symmetry is now no longer a symmetry. In other words, it's violated. It's anomalous. Here's the peculiar thing about anomalies. I mean, this Chern class is pretty, well, I mean, it's pretty concrete object mathematically. I mean, you could set up sort of, so if you were doing what's called BRST, then you'd actually find these classes in the first cohomology of that operator, called the BRST operator. And this just means that,
yeah, I still don't quite get what these Chern classes are, essentially.
So here, do you see where it came in? It just came in because our D operator has the vector potential inside it. And so if you square this, then you just generate the curvature.
Right, okay.
Right, so this is gamma mu d mu, gamma mu d mu, and then you see you take the commutator, you get the d squared, and then you get gamma gamma, which is just 1, right? So you have the anti-commutator term and you have the commutator term. The commutator term is going to give you the commutator of the covariant derivatives, which is going to give you the f, basically.
Right, okay.
Right, now of course, if you had, yeah, this part would be the same, no matter how many dimensions you're in. What changes is when you bring it down from the exponential here, right? So which term survives this m goes to infinity limit? Right. So here it's just going to be the leading term in this Taylor expansion, right? But in higher dimensions, it'll be the higher terms, and those higher terms all come from higher and higher powers of this f, right? And then you're going to have to trace over it. So the one that survives is going to be the d over second Chern class.
Okay.
Right. So this, again, this is maybe a little bit of a regularization dependent way of telling the story. But what I was trying to convey was that it's actually not regularization dependent, as in the form of these anomalies in terms of the background fields, in terms of these gauge fields, is fixed. And it really comes from this weird fact about gauge invariances is that even though they can be anomalous, the way in which they're violated is controlled. This is because of something called the Wezemino consistency conditions, but really it's because they're all classified. These anomalies are all classified by the first cohomology of this BRST differential, as it's called, and that is related to Chevalier-Eilenberg complex. So let's not go there. But this is just to give you the sense that even if gauge invariances are violated, they're violated in some controlled way in local quantum field theories.
So in mathematical terms, if you have a line bundle, right? You want to know what the Chern class of the line bundle is, right? So there's a correspondence between line bundles and invertible sheaves. So I mean, I don't want to go. I don't know if you.
I don't know what a sheaf is. Definitely not.
Okay.
I definitely don't know what a sheaf is. I mean, I've tried. I used to know several times in the past.
Yeah. So we'll see. So if you attend the Hodge theory lectures, then you know what a sheaf is. Okay.
Great.
So I won't say sheaf. I'll say divisor. So a divisor is, you can think of it as a codimension one submanifold. So a hypersurface, right? So there's a correspondence between line bundles and hypersurfaces, and that gives you an element in the first cohomology. And here you use Dirham's theorem, which says that your Dirham cohomology is actually isomorphic to your Betti cohomology. Because you're in a smooth manifold over here. So I mean that's one of the fascinating. Is just an aspect of nature that Dirham cohomology just measures smooth forms on your manifold, but Betti cohomology tells you about the global. So the topology of the manifold. So one thing is local, the other thing is global, and they're all isomorphic. So that's the marvel of nature, and that's basically what he's using there to give you a cohomology class from the line bundle. That's what the Chern class does.
Thanks.
I see. Okay.
But yeah, that's actually that actually captures a lot of what I was trying to convey in terms of intuition here. That there is something global about what it is these anomalies are, and given how we started, we were just talking about. Okay, so this is a bit of a spoiler, and I didn't actually get here, but this expression here is actually specialization of or it's just one version of the index theorem, of the Atiyah-Singer index theorem, because these are the left and right hand. So these are the number of zero modes, left and right-handed zero modes of the Dirac operator. These derivatives, basically, and their difference is given in terms of this Chern class. It's just, again, written in some different notation. You see, and of course, like the index theorem isn't something merely local, right? And so, so there's this interesting connection between between anomalies and sort of the somewhat more global structures involved. Right. So somehow, quantum theory reveals more of the point of having, or of thinking of gauge fields in terms of these bundles over space-time or whatever. That it's not just some trick that you could do away with. You're sort of forced to confront it, and this is very relevant for the project of classifying topological phases of matter. Because when you talk about topological phases of matter, that's exactly what's happening. You just can't do anything local to tell them apart. You really do need this additional information.
Right.
And, so that's what all this will eventually build up to.
Okay.
Great. So again, as I was saying before, just take this to be constant electric field. And then just integrate over space, in other words, and then you get the equation we had before, where you just write your current as current density and vector and whatever. So these are sort of the same statement. Okay, so you see here that that up until we introduced the regulator, it looked like we were able to get away with this. Right? It looked like we would almost get this axial symmetry to come out of the quantum theory, but the regulator just wouldn't allow that. Now you could wonder, would this happen if we weren't just looking at a sort of free theory? So say we were interested in having, like studying an interacting theory non-perturbatively. The only method we know, or the most reliable one, is to put it on a lattice. And so you actually find a completely independent track that lets you discover all of this. So you see, the axial anomaly in the weak sector, as I said, is important for processes like, it is important to tell you about how the EDA meson gained its mass, right? And then you have other anomalies that could tell you about sort of baryon number non-conservation in the early universe or something. So there are a lot of important particle physics questions that you would want to answer by being able to do these QCD calculations. So you really have to deal with the you have to really deal with an interacting theory at the non-perturbative level, and you really need some tools to do that. So normally you would go to the lattice. Now the lattice just doesn't like chiral fermions, right? So there's many ways to see that, but the one that's of most relevance to us, so I've borrowed this slide from Kaplan's talk, The World is a Topological Insulator. I highly recommend it. But yeah, anyway, he's sort of explaining the Nielsen Ninomiya theorem, as it's called. So say you actually, okay, so you're in some even dimensions, 2K, and you want to regulate the theory of Dirac fermions, right? So there's interaction terms here too, but okay, this is just focus on the kinetic term. These guys proved a theorem saying that you can't have all four of these properties, right? So very conveniently, Kaplan sort of like highlighted what the implications of each of these properties are. So d tootles of P is basically your regulated kinetic term. So what do I mean by lattice regularization? Well, really you're taking your space and then you're replacing it with a regular lattice, which means that all your derivative operators are going to be are going to look like differences now, finite differences, right? So if you wanted to say psi minus p, so if I was doing this in position space, I would be like psi sub x, where x is now a point, so it's a xi, a vertex of the lattice, and psi sub j are my two terms. But I want to take the derivative of psi sub j, which means that it's really psi sub j plus 1 minus psi sub j minus 1 over 2. That's one example of a regulated derivative operator. But whatever, you could introduce it in many ways. Generally, though, you could just say that in momentum space, it would look like this, right? I have d total p. So in momentum space, I'm just going to be doing the sort of finite Fourier transform. It's really like just Fourier series, right? So what you can't have is for d to be this periodic analytic function of p, which means that it's regulated and local. You can't have it be, or you can't have it be linear in p for small values of p, which is what it means to have Dirac-like behavior at long wavelengths, right? Because the Fourier transform of p is the linear derivative operator. And then this is the thing that everybody keeps. So this is the one that everyone sacrifices in most practical applications. For d to be invertible everywhere except at p equals 0, which means that you don't, okay, so in Euclidean signature, there's only one pole, the propagator, right? That's at p equals 0, and that tells you what the mass of the particle that's propagating is, right? Now, if you have more than one pole, it's just telling you that you have more than one fermion, and you don't want that. Right. But people say, okay, well, bite the bullet. So you have what's called fermion doubling. It's not necessarily just doubling, though. You could have quadrupling and so on. So in the continuum, if you choose D2 naively, you might end up with like 12 fermions. You just wanted one. And here, big gamma is our gamma 5. And this is just a statement that it respects chiral symmetry. So you see, you don't want doublers, you have to violate this. So you want the first two properties, come what may, right? It would be really hard to reconstruct any physics of interest without the first two properties. So either you maintain chiral symmetry and then have doublers, or you have doublers and then, or sorry, yeah, or you don't have doublers and then you violate chiral symmetry. but you can't have all of these. And this is how the lattice is telling you you're gonna see an anomaly, right? So, having doublers is just a way of taking your anomaly from the violation of the void identity to just having a different number of fields. They're sort of, they correspond to each other. If you didn't have the second property, you're not doing relativistic field theory anymore, so you don't really care. You're out of this game, right? And if you don't have the first property, you're not running your simulation. It's just going to blow up all of a sudden, so you can't even start. So this is a more sort of invariant statement, or sort of a more general statement, that even in interacting theories, you're going to see this anomaly. In other words, if you have an anomaly that's sort of possible, right? Again, these anomalies are classified in some way corresponding to some cohomology and all this, but whatever. Say that there's an anomaly you can conceive of, right? That in the continuum, right? On the lattice, that symmetry has to be broken explicitly. If it's not broken explicitly, you're not going to see that there's going to be an anomaly in the continuum. Right? So it's the same thing about the regulator before, right? The regulator just explicitly violated your symmetry. So of course you're going to see some extra terms in the void identity because, well, you don't have the symmetry anymore, right? So that was what our heat kernel did for us in giving us this term. So yeah, in the end, it's just to say that the anomaly is inevitable.
Right.
And how you could see this, right, this is what, again, I borrowed this example from Kaplan's talk. This is like Hilbert's hotel. So the vacuum in the continuum. So if I was just looking at the Dirac C picture, you can mine it forever. Like, you introduce an electric field, you can mine it forever. You just keep producing left-handed modes or right-handed modes. It keeps giving. It's like Hilbert's hotel. You can always just move over one, right? You take, like, if you wanted to map sort of like, 1 to infinity to, like, 2, 4, 6 all the way to infinity, you could just do this by, whatever. So on the lattice, there isn't enough room to do that. I mean, the symmetry is just going to be broken.
Yeah.
Right? So this is how a lot of the interest in these anomalies was first sparked. This is what people initially wanted to do. They wanted to be able to regulate chiral theories and do simulations of, like, chiral gauge theories and whatever.
So
and they found
Kaplan a mathematician or what?
No, he's a physicist.
No guy called Kaplan, and he's a Hodge theorist.
No, not at all.
Yeah. Okay. And do you guys spell Euclidean with an I or what?
I guess he does.
Okay. Yeah, it should be an E. Yeah.
Okay. And I don't know what I did,
Okay.
but I actually don't pay too much attention, so I might do both. Yeah, but anyway, this is okay. This is sort of how you meet anomalies from the high energy physics point of view.
Right.
Now, we were just talking about this chiral symmetry. You don't have a good reason to. Okay, so in the context of interest, you don't have a good reason to want it so badly. Like, you're not really worried that it's broken. You could treat it like a symmetry and that it's violated by the quantum theory. Fine, right? It's not a problem. If you had such an anomaly for your gauge group, so you can't have things known as gauge anomalies. That's a problem, right? It just means that you're not quantizing the right thing, or you're not getting the right quantum theory out of your quantization procedure. You're getting a quantum theory of something else. Right? So that's sort of a problem. And this is why anomalies were such a problem in string theory. So in string theory, everyone talks about the conformal anomaly. Really, in the superstring case, it's some mixed anomaly. There's gravitation, so it's very messy. But naively, part of it's going to be what's called the Weil anomaly, or the conformal anomaly. Now, when we were talking about conformal field theories how many ever days back, we saw that by and large, conformal field theories are classified by the anomaly coefficient. So you don't really care that they're anomalous, right? You know, that's just part of the OPE algebra. It's fine, whatever. I know what it does, right? I can just proceed. But that's because you interpret conformal symmetry as a symmetry of that system, right? You're not seeing it as a gauge invariant. Now in string theory, the conformal symmetry of what's called the world sheet is coming from a gauge invariance, which would have been diffeomorphism invariance of the theory that it really came from. The string theory is secretly a gravitational theory along the world sheet. And you don't want that to be anomalous. So the conformal anomaly is really telling you that you aren't representing the diffeomorphism invariance at the quantum level properly. Mm-hmm. So there you really need it to be canceled. You need to turn some knobs and hope that it gets canceled. Whereas here, well, you could say it's not that much of a problem. But you could take issue with it. I mean, you could say, well, where is this charge going? Right? What's going on with this? And that's where this mechanism of inflow comes in. I don't think we'd get this far. I mean, we could save this for another time, but this is related to U1 Chern-Simons theory. And sort of very quickly, I mean, I didn't even finish my notes about this, but very quickly, you cook up a three-dimensional bulk, okay? And on this three-dimensional bulk, you write down this abelian Chern-Simons action. So remember, we didn't give any life to this gauge field in our two-dimensional system, right? It didn't have any dynamics. But say we gave it dynamics, but this dynamics extended into some one additional dimension. Now what you find is that you could ask, okay, well, what happens to this theory under a local U1 transformation? Right? That's what this gauge transformation is here. Sorry. So omega depends on x. And you find that this isn't strictly invariant, right? It's invariant up to a boundary term. Right? If this were S3, you'd be fine, you wouldn't care. Right? But here you really think that this is like a half space. This is like R3 with a R3 plus or whatever you want to call it. And that on the boundary sits the system that you had before. And notice that the form of this, so if I integrate it by parts, then what remains of this boundary variation is exactly what we had before, epsilon f. Right, so trace f. In other words, you could pass this off, right? But by tuning the coefficient of the Chern-Simons action, we could pass this off to a bulk.
It's a boundary.
So this is the mechanism of anomaly inflow. So you're saying that, you know, the 3 dimensions, there is no anomaly because there's no chirality, right? So what happens in odd dimensions is that, okay, you have your Clifford algebra. In even dimensions, you can form this chiral generator gamma 5. In odd dimensions, the next odd dimension, take the lower dimensional gamma 5 and make it an additional gamma matrix. That's all, right? But there's no chirality anymore. So if your total system is 3-dimensional, there can't be an anomaly, right? So this is a bit more of an intricate way to cancel the anomaly, so to speak. They just introduce this bulk that has this Chern-Simons theory that operates in it. And in fact, this is what's powering the so-called integer quantum Hall effect. And there, what you actually find is that the conductivity is quantized. You find a system in which you have this conductivity that's quantized in certain levels. And the conductivity is a response coefficient that relates current and the electric field. Right?
Yeah.
Kind of like this, current and electric field. Yeah?
Sorry, I'm going to push off right now. So
okay, man.
To continue.
Yeah, sure. I mean, this is just going to be, there isn't much I'm going to say here on. Thanks for joining.
Yeah, okay.
I'll join on Saturdays too.
Yeah, it was. Yeah, sure.
See you.
See you.
See you, Ben. All right.
Bye.
So what you find is that the quantized conductivity corresponds to the quantization of the Chern-Simons level K.
Oh.
And yeah, this is these are
Next week,
spoilers
I
for
guess.
next time. Yeah, yeah.
Okay.
Great. So I guess I'll stop screen sharing now. Are there any more questions? What's
I have to still think about like I get how like the Chern's class comes into this and all of that story, all of that, but yeah, more from the math side, I guess. I want to understand it a bit better. Yeah, I guess.
it would be very fun to have Dan explain to us exactly what he meant by saying that you can realize this line bundle construction as some kind of divisor or some sheet, you know.
Right.
So just to see how.
Yeah, I did not get any of that, but yeah.
Well, I mean, the basic intuition is that you're going from the level of something that's analytic, which means it could know about differential properties of some smooth manifold, or something algebraic,
Right.
you know, something that's just encoded in the bones of the theory, something more global.
Right.
Right, and this is actually what's cool about all this is how quantum theory exposes the more global aspects of this geometry, right? Really, yeah, you're sort of uncovering the geometry of that of that line bundle. You see that it actually matters. I mean, you need to know. So things like the Chern class actually tell you whether you have a trivial bundle or not, right? The level is actually telling you whether or not you have you know, simple vibration, or if you have some twists and turns along the way. And you see quantum theory that exposes all of these things. Right, so anomalies do it, but so do instantons. Right, so if you're doing gauge theories, you would say that, oh, this non-trivial bundle structure is really revealed by the structure of the vacuum degeneracy of the theory. So yeah, it's well, I mean, this is what quantum field theory has really led to now. It's the study of how these structures are illuminated, so to speak.
It's so fascinating.
Anyway, I'll stop the recording now.
Recording, yeah.
Yeah.